All right, today we're going to finish up 2-3, talking about the squeeze theorem, and then start 2-4, talking about continuity. All right, so here's a theorem just to start off with. If f of x is less than or equal to g of x, when x is near a, and the limits of f and g both exist as x approaches a, then we could say the limit as x approaches a of f of x is less than or equal to the limit as x approaches a of g of x. Okay, so if we know this about the functions, and we know it's true when x approaches a or is near a, and both limits exist, then we could say that this is true. This will help us when we look at the squeeze theorem. Here's what the squeeze theorem says. The squeeze theorem says if the function x is less than or equal to the function g is less than or equal to the function h when x is near a, and the limit as x approaches a of f of x equals the limit as x approaches a of h of x equals L, so these two limits are equivalent, then what we could say is the limit as x approaches a of g of x is L. So see how that g of x is being squeezed in the middle? If these two limits are equivalent, then that third middle limit would be equivalent. Let's look at an example of that. I would like you to show that the limit as x approaches 0 of the function x squared sine 1 over x is 0. So I want you to show the limit of this as x approaches 0 is 0. Well, the first thing you might think about is to use one of your limit laws. And we're going to try to say, well, let's look at the limit as x approaches 0 of x squared times the limit as x approaches 0 of sine 1 over x. And that would be great if we just had this part, because we know this limit would be 0. But here I can't take this limit because I can't take 1 divided by 0. It doesn't exist. So we're going to have to do something else. And what we're going to do is we're going to look at, well, let's look at just the function sine x. Think about sine x and what it looks like graphically. And we know graphically above it's bounded by positive 1 and below it's bounded by negative 1. So if we think about that graph of sine x, okay, above it's bounded by positive 1 and below it's bounded by negative 1. Just thinking about the graph of sine x. Okay. Well, if we know that to be true, we could say negative 1 is less than or equal to sine x, which is less than or equal to 1. And we could say the same for negative 1 is less than or equal to sine of 1 over x is less than or equal to 1, because there's no amplitude change and there's no shift up or down. We know no matter what, we're bounded by a positive 1 up top and a negative 1 down below. All right, but our original function had this x squared in it. So let's go ahead and multiply this x squared into the bounded function. So we're going to take our bounded function and multiply it by x squared. Now this is kind of weird. I used one soft bracket and one hard bracket. Let's change that. Okay, so I'm going to take x squared and I'm going to give it to all three of those. Okay, so this is going to become negative x squared is less than or equal to x squared times sine 1 over x is less than or equal to x squared. And we already said the limit as x approaches 0 of x squared is 0. And the limit as x approaches 0 of negative x squared would be 0. So by the squeeze theorem, if this limit here is 0 and this limit here is 0, then this middle limit would have to be 0. So the limit as x approaches 0 of x squared times sine 1 over x is 0. Okay? So notice what we did here. We took the limit of this piece, the limit of this piece, the limit of that piece. And we found that this limit was 0. And we found that this limit was 0. So this middle limit is 0 as well because of the squeeze theorem. And that was just finishing up lesson 2-3. Today we're also going to move on and talk about part of 2.4, and we're talking about continuity. And let's just think about continuity, everyday language. Okay, so let's think about a continuous process is one that takes place gradually without interruption or abrupt change. So sometimes when we see math words, we could think about what we know the word means in everyday language and see if we could kind of apply it. Well, by definition, a function is continuous at a number a if the limit as x approaches a of f of x is f of a. And here are kind of the requirements of what it means to be continuous. F of a is defined, meaning a is in the domain. The limit as x approaches a of f of x has to exist, and the limit as x approaches a of f of x equals f of a. So those are kind of the three requirements we have. I think the easiest way to kind of connect your everyday language of a continuous process and what it means to be continuous when we're talking about math is think about it graphically. The graph can be drawn without removing your pencil from the paper. So it's continuous. I don't need to pick my pencil up and jump up or anything like that. So I think when we look at it graphically, it really helps us to piece together what it means to be continuous. What we're going to do now is we're going to look at some non-continuous functions, and we're going to look at them graphically, and then we're going to also look at what the function is. Okay? So if I look at this function, if I went to draw this, notice I can start down here at wherever. It goes on and on. Go, 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 go. I'd have to pick my pencil up and put it down and go again. Okay? So this function, which algebraically is f of x equals x squared minus x minus 2 all over x minus 2. Think about what that domain would be. This function here, here's the function, here's the graph of it, is discontinuous. And we could also say it is called, has a removable discontinuity. Okay, it's removable discontinuity. This function here is discontinuous as well, because I'm going to go from here, go, 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 go. But then I'm going to have to lift my pencil up and come back over and go. Okay, so this is also a discontinuous graph. This graph is the graph of f of x equals 1 over x squared. And this is called infinite discontinuity. So notice how I'm going up infinitely, going down infinitely, or going up infinitely, I guess you would say. Okay, so this is infinite discontinuity in part B. Part C actually has the same type of discontinuity as part A, okay? Both of these have removable discontinuity, okay? This graph C is the function f of x equals x squared minus x minus 2 over x minus 2 if x does not equal 2, and f of x equals 1 if x equals 2. Okay? But these both have removable discontinuity. Where part D is a step function, f of x equals x. Okay, and we're saying it's a step function, so it has these double hard brackets here. And this is called jump discontinuity because the function jumps from one value to another. So I'm going here, and then I'm jumping up. And I'm going here, and I'm jumping up to here. And I'm going here, and it would probably continue on and on and on. Okay? So those are the three types of discontinuities we'll talk about: removable, infinite, and jump. Okay? We could also talk about a function being continuous from the left or the right. A function is continuous from the right at a number if the limit as x approaches a from the positive side of f of x equals f of a. Okay, so it's continuous from the right if the limit as x approaches a from the positive side of f of x is f of a. And then it's going to be continuous from the right at a number if the limit as x approaches a from the negative side of f of x is f of a. And when I'm saying negative side and positive side, so positive side would be like coming from the right, going that way. And coming from the negative side would be starting at the left and going to the right. And we've kind of already talked about that. Okay? A function is continuous on an interval if it's continuous at every number in the interval. Okay? And let's kind of take a look at an example of that. Let's take a look at an example of that. Hold on one second, I lost that page.